Hello and welcome to another episode of Physics Problem Solving. We're looking at another question from a 2024 physics subject exam for electrodynamics. This is question 5, a charged ring surrounding a slowly charging solenoid. I will give you a second to look at the problem, and then I'll come back after a short transition and have some more notes and read the problem aloud. Welcome back. I hope you had a chance to take an attempt at the problem. I'll go ahead and read it for us. A long solenoid with radius A and length L has n total turns. A uniformly charged ring with a uniform mass distribution with charge to mass ratio Q over M of radius B, where B is greater than A, is concentric to and surrounds the center waist of the solenoid. The current in the solenoid slowly increases from time t equals 0 in the following way. After a long time, the charged ring is rotating with angular velocity omega. What is the magnitude and direction of omega? Note that the moment of inertia of the ring is mv squared. Clearly define your coordinate system and articulate any approximations you may use in calculating omega. So this is a lot to digest. There is a solenoid and a ring concentric around it, which I've drawn in this picture here. I've also labeled our coordinate system. We have z, r, and phi hat into the page. There are three kind of main approximations here. We have the long solenoid that is saying that its length, which is distance L, is much longer than the radius A. We also have slowly in regards to how the current changes. And that is just to say that we don't want any variations in the electric field. Officially, it's these statements over here that the speed of light times the characteristic time frame tau of the current is much larger than the length L, and also much larger than that should be a B, I apologize, the radius of the ring. There's no fields oscillating in between these. And then we also have after a long time, which I take as t goes to infinity. You can also say that t will eventually be much larger than tau. All of this setup is just to get us to the fact that we can use a infinite solenoid approximation. And that gives us the magnetic field inside the solenoid is mu naught times the number of turns over the length of the solenoid times the current inside of the solenoid. With all the setup to get the infinite solenoid approximation, we can now begin to kind of think about the problem. We have this solenoid creating a magnetic field through the center axis of both the solenoid and the ring, but we have this expectation that the ring will end up rotating. And we have a changing magnetic field, so this is dB of t dt. This equals something, and hopefully if you have your Maxwell's equations pretty well memorized, you can say that the negative dV dt equals del cross E. And hopefully that is enough to get you in the right mindset of how this ring is going to start rotating. And of course, right as we're getting started, there's another little tricky aspect. We have this del cross E, but that isn't entirely helpful to us. We actually want to use the curl theorem and do del cross E dA. I'm going to rearrange a few things while we're doing this. Integral negative magnetic field with respect to time over the area. And we're going to keep moving down, but this is now me using the curl theorem, but you kind of have to see it beforehand. This will give us E dot dl, and that will still be equal to the cross-sectional area of the magnetic field, dB dt dA. On the left-hand side, we're just calculating the electric field on the ring, and that is not changing with respect to the integral, so we can actually pull the electric field out. And we know this is going to be a 0 to 2 pi d phi, since that is the direction of our integral. And this is going to give us a 2 pi r, and that r is going to be on the ring, so we're going to end up with a b. On the other side, we're going to have the area that the magnetic field is going through, which is the double integral, change in magnetic field, change in time, over the area. And we said the cross-sectional area of the magnetic field, that's just going to give us a pi a squared. There's that negative out front. And then we have the change in magnetic field with the change in time. So now we have E is equal to negative a squared over 2b dB over dt. So the only thing we're left uncertain about in terms of defining E is this dB dt, but we can do that pretty simply. We'll take dB dt, and again, using the equation for the infinite solenoid, we have mu naught n over L, and then we have di dt. And this was given in the problem, so it just ends up being mu naught n over L. We have an I naught over tau, and then e to the negative t over tau. Awesome, let's shore all of this up. We have E, again, we already kind of defined it in the phi hat direction, is negative a squared over 2b times mu naught n over L, I naught over tau, e to the negative t over tau. And that is kind of our first answer. We're going to clean the whiteboard up a little bit and come back to it. All right, we're back, and we're now looking at how this electric field is applying a force. Well, good thing the ring is charged. We can use just F is the total of the electric field acting on microscopic charges, if you will, or charge segments. We do have to get a rotation, but hopefully we can use force and torque. So the radius across the force, that's how we define torque, but torque can also be defined as the change in moment of inertia times rotational velocity with respect to time. And hopefully we can see that our final answer is sitting right there. So let's get into it. I'm going to rearrange some things. Integral r cross phi hat. And this radius is going to be the radius of the ring times the electric field, dq. And this is still an integral over dq. And that is going to be equal to the derivative of the moment of inertia times rotational frequency with respect to time, where dq is going to be equal to q over 2 pi b, which is the radius of the ring. And then we also have b d phi. Since this is an angular integral, these b's are going to cancel. And now we can use that and plug it into our equation that we have. I'm going to do this cross product real quick. We have r hat cross phi hat. That's going to give us a z hat. We can pull that out front. And then we have the integral of b times e q over 2 pi. And this is d phi. Since we're just integrating over one ring, we're going to have 0 to 2 pi. And this is still equal to the same portion over here. Change in I omega over dt. Looking at our electric field, it actually doesn't change with respect to phi. There's no phi variables. So we can pull all of that out, or we can just do the integral 0 to 2 pi. That's going to actually cancel this 2 pi. So we now have, again, everything is going to be in the z hat. We have b times e times q, and that is going to be equal to the changing torque, which we can also pull the I out of here, and the question says it's mb squared, so b squared m d of omega dt. With our final answer in sight, we can start looking at separating the omega. I'm also going to drop this z hat here. We know everything is happening in this plane. So we have b eq over b squared m. Cancel out some b's. And now all that's left to do is to integrate over time and get our just omega. So the integral of time, we said earlier we could do the from 0 to infinity of d omega dt is going to be q over bm times e, which we know is of time, from 0 to infinity. After a quick integral on the left side and a copy and paste of e on the right side, I have this pretty simple Gaussian integral. But besides that, we have all of these constants, which I don't exactly want to write down right now. But this will just give us 0 minus, and then that's going to be negative tau. And just for completeness, I'll write out the final answer. Omega in the z hat direction is going to be negative mu naught over 2. We end up with an a squared over b squared, q over m, which is the charge to mass ratio, n over L, it's from the beginning, and then that we actually remove that tau from this tau right here, cancels with that guy, and we get I naught all in the z hat direction.